Fundamental and derived units. The fundamental units are also referred to as the SI units of measurement. In order for measurements to be understood universally, 7 independent quantities were identified and given units to form the basis of the SI system of measurement in 1960. So these units are the mass, and the unit of measurement for mass is kilogram. So that is the symbol kg. Then we have the length. The length is meter, and the symbol is lowercase m. Then time is measured in seconds, and the symbol is lowercase s. Temperature is Kelvin, and the symbol for temperature for Kelvin is the uppercase K. Then electric current is ampere. We have the lowercase a. Then we have luminous intensity, which is candela, and the symbol is CD. Then the amount of substance is mole, and this is the symbol. Now, these are called the basic units or the fundamental units of measurement. Now let's talk about the derived units. There are some units which are made up from multiples and combinations. So multiples and combinations of the basic units. And these are called the derived units. So these are the examples. We have kilo, then this is the symbol, and this is the multiple. Then we have mega, giga, tera, then and so on and so forth. So these are called the multiples of units, or they are called the derived units because they are obtained by combining 2 or more basic units, which are the fundamental units of measurement. Now let's take an example from WASI 2016 NOVDEC. This is question 8. Which of the following is most suitable for the measurement of the diameter of a thin wire? So we know the micrometer screw gauge. Micrometer screw gauge is used to measure the diameter of a thin wire. Therefore, the correct answer is option D. This is the correct answer. Now let's look at another example from SSCE to 1997. SSCE 1997. We are supposed to state 3 fundamental units of measurement, and also we are supposed to define what a derived unit is. So let's look at the solution. Now we've looked at various fundamental units, so we can mention any of them. So 2 of the fundamental units are the kilogram, measured in the kilogram, and the symbol is kg. Then we also have the Kelvin, which is the symbol is uppercase K. So we have time, and time is measured in seconds. So this is the third example, time in seconds. Then also we are supposed to define a derived unit. A derived unit is a combination of two or more fundamental units. Now we want to write down the dimensions of the following physical quantities. So we know acceleration, so we need to express this in terms of the basic or the fundamental quantities. So we know acceleration is equal to velocity over time. Then we also know that the velocity is measured in terms of that is length per time. So we have length per time over time. Now this will simplify to from indices. This is 1, this is exponent 1 here, so this comes up to give us length per time, which is length per time squared. So that is the derived unit for acceleration. Now let's talk about pressure. Now we know pressure is force per unit area. And we know force is mass times acceleration. Force is mass times acceleration. Mass times acceleration, that is ma. Then area, then we have area over here Now we know mass is measured in mass is already a basic quantity, so we have this. Then we've realized that acceleration is length per time squared, over area. But area is unit squared or length squared. Then this to simplify this, so this is raised to the exponent of 1 and this is raised to the exponent of 2. So when we simplify this, we get mass per length, then per time squared. So that is the derived unit for pressure. Now let's talk about density. We know density is mass per unit volume. Then mass is already a basic quantity. or basic unit. So mass per volume, so we need to convert the volume to basic unit. So the volume will be, in terms of basic unit, is going to be length cube. So we have m over length cube. That will give us the volume. So this simplifies to mass per length cube. So the derived quantity or the dimension of density is mass per length cube. Then the dimension for pressure is mass per length per time squared. Then the dimension for acceleration is length per time squared. Now let's take another one from SSC 1993. Define density of a substance. So you know the density of a substance is defined as mass per unit volume of the substance. Then if 25 centimeter cube of a quantity of marble has a mass of 45 grams, calculate the density of the marble in kilograms per meters cube. So they specify our unit for the density, which is kilograms per meters cube. So we need to convert 25 centimeter cube and 45 grams. So 45 grams must be converted to kilograms. So 45 grams is equal to 45 over 1000, which is 10 cube, and that will give us 45 times 10 exponent negative 3 kilograms. And we must also convert the 25 centimeter cube to meters cube. So 25 centimeter cube, we know that so we need to convert this to, this is cube, and we need to convert it to meters cube. So that will be equal to 25 over 10 exponent 6, which is 1 million, and this is the same as 25 times 10 exponent negative 6 meters cube. Now, so we got this because 100 centimeters make 1 meter, and in terms of cubic we need to cube both sides. So 100 times 100 times 100 will give us the 1 million, which is 10 exponent 6. Now this is the unit in meters cube, and this is the unit in kilograms. We need to express the density in terms of kilograms per meters cube, and we know that density is equal to mass per unit volume. Mass per unit volume, and we know the mass here is 45 times 10 exponent negative 3, then all over the volume, which is 25, times 10 exponent negative 6. So we simplify this to obtain. So 45 over 25 will give us 1.8. And 10 exponent negative 3 divided by 10 exponent negative 6. So the laws of indices is to subtract, giving us negative 3 plus 6, and that will give us 10 to keep the base, and subtract the exponent, which will give us 10 exponent 3, because negative 3 minus 6 is the same as 6 minus 3, and this is in kilograms per meters cube. Kilograms per meters cube as required.